History Feather.
All right. So far, we've been taking a look at things like moment of inertia and center of mass, and we're going to start bringing these things together now. We need to introduce one more idea, this idea of torque. Now, when we took a look at translational kinetic energy, it's 1/2 mv squared. And then we saw with rotational kinetic energy, we introduced this new idea of moment of inertia. And the rotational kinetic energy is 1/2 I omega squared, where I takes the place of mass for rotation, and moment of inertia replaces mass. And instead of speed, we have angular speed, right? Well, we've studied energy so far. We've also studied Newton's second law. It's about all we've studied so far. And we saw that the sum of the forces equals mass times acceleration. So forces cause acceleration. Forces do not cause velocity. We never said the sum of the forces equals mass times velocity. They don't cause velocity. You don't need forces for velocity, right? So in rotation, we had the sum of the torques equal moment of inertia times angular acceleration, where again, our mass is being replaced by this thing called moment of inertia. And torques do not cause angular motion, they cause changes in angular motion, right? So, so what is this torque thing? Well, you kind of know what it is. At some level you do, because you've all opened doors and things like that. Many of you probably use wrenches and things like that. But basically, if I have a book like this, right? I have a book. I don't have a door handy, but I do have a book. And if I wanted to open this book, it's Andy Goldsworthy collaboration with nature. Fine photographs. If you hold it like this, if I want to open this, if I apply a force like this, it's not going to open, right? It's not. I don't care how hard you push, it's not going to open because there's a hinge here, and you know that if I push in the direction of the hinge, it's not going to open. So what I need to do, of course, is push at right angles. And there you go. I go from no rotation to rotation. So I gave it an angular acceleration. So I opened it, right? And I also could open it by pushing it farther in, but it's a lot harder. It's really tough on the fingers. Oh, right? I could even do it way inside. Way inside. I would probably break my finger. I bet it. No, I didn't break it, but it was pretty hard to open it from there. So that's torque. And basically what torque says is if you want to change the angular rotation of something, you need to apply a force at right angles, or at least it needs a component at right angles relative to the position vector from the pivot point. It's going to be the product of how far you are from the pivot point and how much it's at a right angle. Let's take a look at that. So torque, in your book, they gave a definition, which the early definition I didn't like so much. It's true, but I didn't like it. I like this one, R cross F. This is also in your book. I don't know that you made it to that point in your reading, where we use, it's a fancy mathematical way. It's using the vector cross product to say the torque equals R cross F. So let's take a look and see what that means. All right, so let's say I have some random object, looks like this, and I have a hinge right there, and so this is the pivot point, and I want to spin this thing, give it angular acceleration. So what I'm going to do is I'm going to apply a force, a blue force like this, like that. Torque is going to be R cross F, which is going to be the R times the perpendicular component of F. Let me draw the R vector, the position vector, from our pivot point. I'm going to go like that. I'm going to say that is R. That's my position vector, R. And let me say that, all right, let's say I knew this angle. let's say I knew that angle theta. I don't know what angle you're going to know. You're going to need to know some angle though. So I'm applying a force like that. Only the right angle component of F will actually cause a torque. So only this component right here. I'm going to do the parallelogram method. Here is F, perpendicular. That's perpendicular to R. It also has a component F parallel. Those two vectors, I didn't draw that very well, but I ran out of space. But you get the idea. This is the only component of the force that actually contributes to, is that a right angle? Yeah, why not? All right, close enough. So what are we going to do? How are we going to calculate this thing? Well, we're just going to take R and multiply it by F. It looks like this is going to be cosine of theta, right? This is the adjacent side of the right triangle, F cosine theta. That's going to be the magnitude of the torque. I should put magnitude. This is not the magnitude, but this calculation just gives us the magnitude. In this problem, since it's kind of wants to maybe cause it to rotate this way, we're going to say this is positive in this case. That's in the positive direction. I'm going to talk about a little bit more about direction in a moment. All right. Well, that's one way to calculate it. The other way you could calculate it is we could take the torque is R perpendicular times F. So rather than taking the perpendicular of F, component of F, we'll take the perpendicular component of R. All right, so let's see what that looks like. First thing I'm going to do is I'm going to draw the line of action, right? So I'm going to take F, and that's called the line of action. I drew it through the force. Force is where the action is, not position. Position just is there, but force is where the action is. So there we go. That's a line of action. What color should I use? I'll use green. Green. So what I'm going to do is I'm going to draw the component that is perpendicular to the line of action of R, which is there. I will call that R perpendicular. And of course, R also has a parallel component, although we're not going to be interested at all in that. We're only interested in the perpendicular component. This is also called the moment arm. It's called the moment arm, right? That's the moment arm. So that's going to be a really important idea. Being able to calculate the moment arm is going to be really useful for us. So here we go. All right, let's take a look at our angles here. We had, this is a 90-degree angle, even though it might not look like it. Yeah. And I'll call this phi. These are complements. Therefore, this must be theta because these have to add up to be 90. Those have to be add up to 90. All right, so that's theta. So this, it turns out, is R perpendicular is R cosine of theta, and then multiply to F. And we notice that we get the same answer that we had before when we went RF perpendicular, RF cosine theta. Here we also have RF cosine theta, right? So it gives us the same answer at the magnitude. And in this case, the direction would be positive. All right, let's talk more formally about the direction of the torque. We give positive and negative, like, you know, if I have something and if it's rotating this way, we tend to say it's positive, and this way is negative. That's good for calculations and things like that. But the problem is, which way is positive and negative depends on where you are. If I'm standing right here and looking at it, it's one way. If I was on the other side of the board and looking the other way, I would get a different answer. So we need an unambiguous answer. So the vector cross product does that. We're going to have to use the right-hand rule. So we have our new object, and we have a pivot point right there, and we're going to apply a force like this, I'll apply a force like that. There's my force vector. Get rid of this stuff. So the torque is R cross F, where we talked about how to get the magnitude. Let's get the direction. I'm going to draw the position vector. I'm going to redraw the force vector so it's right here. Close enough. Close enough to the same vector. There we go. And what we do with the cross product is we take our right hand. Everybody get their right hand up. Everybody's right hand up like that. Right? Vikram, your right hand up. All right. You take your right hand and you can't use your left hand. Can't use the left hand. You gotta use your right hand. And what you're gonna do is you're gonna go R cross F. This is what you're gonna do. You're gonna take your hand and put it in the direction of the first vector, which is R. All right. So I'll go R, and now I have to bend my fingers in the direction of F. I'm gonna use that F down there. Yeah, I can't without snapping them. Don't snap your fingers. Nobody break their fingers. What you want to do, there's an easier way other than snapping them, is to actually turn your hand around like that. And like that, you go R, bend them that way, F. Your thumb will point in the direction of the the result of the cross product. The result of a cross product is another vector. In this case, it's torque. And then in this case, the direction would be into the board. All right, so that'd be a torque into the board. We could calculate the magnitude like we discussed earlier. Into the board, R cross F. It's easier if you put them tail to tail than tip to tail, but you could also have done it that way too and saw that it was that way. Sometimes when they're tip to tail, they can get confusing. But anyways, and note that R cross F is different than F cross R. If I did F cross R, it would be out of the board, and that would be different, right? So in this case, we do that. Into the board is what we call a negative, right? Into the board is what we call negative in our little convention. All right, so we're going to give you a bunch of problems to calculate the torques. You have to get good at calculating torques. I want you to calculate torque probably the more intuitive way, where you just take the perpendicular component of F and multiply by R, but I also want you to do the same thing using the moment arm, where basically you're taking F and multiplying it by the perpendicular component of R, and you have to do that by drawing the line of action. There's the line of action right there. There's the line of action. Look at it, action. All right. We have an object. We pivot about this point. There's a 30 Newton force at an angle of 55 degrees. And let's say that distance, the distance from the pivot point is, let's say, 40 centimeters. What is the torque? We want the direction and the magnitude. Let's do it with the moment arm technique and just finding the perpendicular component of the force technique. All right.
Pause the video now.
The magnitude of the torque is RF perpendicular, which is 0.4 meters times F, which is 30 newtons. But we need just this component of F right here. We want the right angle component, which is F right angle. Those are the two components. So this is going to be the sine of 55 degrees. All right, I don't have a calculator handy. It's whatever that is. All right, let's do it with the moment arm technique. Let me get rid of this. Get rid of those vectors. And I'm going to draw the line of action. There's the line of action. Like that. our perpendicular looks like this. This is our. All right, it looks like we end up with. So if we find, if we say that is r perpendicular times f, well, r perpendicular is 40 centimeters times sine of 55 degrees times 30 newtons. So we see we get the same answer. All right. You need to practice, so drawing this line of action. This is going to be really valuable, and it's going to be really confusing to many of you. The sooner you get this idea of the line of action and this thing, which is called the moment arm, the better off you'll be, the happier you'll be. You have to get this stuff down because rotation can be a mind bender at times. So you have to be, finding torques need to be second nature. All right, good luck. We'll give you some more problems right now. All right, so here we go. We got our object, and here is the pivot point. We want to know the amount of torque around the pivot point. If I apply a force of 20 newtons at an angle of 30 degrees, and it's a distance of 45 centimeters from the pivot point. Why don't you give that a try?
Pause the video now.
So let's first try r times f perpendicular. All right, so r is 0.45 meters, and f perpendicular is going to be 20 newtons times. I want the perpendicular component, right? And that's going to be right there. That's going to be the perpendicular component. This is f perpendicular right here. All right, I want to know what is that value. Well, from here, it is f sine of 30 degrees. F sine of 30 degrees. All right, so I guess that's 0.5. That's 20. So that's 0.5. That's 10. So I guess that would be 0.45 Newton meters. Now, some people will call this meter newtons because a Newton meter are also units of energy. Torque is not energy. They happen to have the same units. So to differentiate it, sometimes people call it meter newtons. It's a Newton meter too, but torque is not energy. They just happen to have the same units. All right. So let's try it with the moment arm. I think this one's intuitively easier and makes sense. Let's just find that. The moment arm is less intuitive, but quite valuable. So let's try this. Let's try r perpendicular times f. So the moment arm times f. So what I'm going to do is first, I'm going to draw the line of action. Right? The action, force is where the action is. Like that. Like that. Alright, so now we need to find the moment arm, the component of r that is perpendicular to that. And it looks like it's going to be like this. Like that. It's the shortest distance to the line of action from the pivot point. Alright. Alright, so on this one we can see that we have a right triangle here. And here's a hypotenuse which is 45 centimeters. So our hypotenuse is 45 centimeters. So our perpendicular is going to be r, here's the opposite side, sine of 30 degrees times f, which is 0.45 meters times the sine of 30 degrees times F, which is 20 newtons. Alright, so we also, again, we got 4.5 meter newtons. Alright, what direction is this? This direction, alright, it's easier, I think, to see by looking at the perpendicular component of the F, but it looks like it's causing a torque kind of in this direction, so this is a negative torque, or into the board. Into the board. Right, we have a torque into the board.
Extreme physics.